Okay, we'll make a start now. Those of you who just did materials lab in Renault building, are you back here yet? Yeah, okay. So we can start now. So this lecture I'll start probably a couple of minutes late every week so that to give people time to come over from Renault to here. Okay, so what am I going to do today? So I gave you few problems to attempt, and those are given as here, equilibrium examples. Did you manage to do that? Okay, so some of you did. Okay, I'll quickly go through that, or at least indicate the solutions to you and upload the full solution later on. But before that, what I thought I would do is go through the free body diagrams, some of these again. So I took some free body diagrams from a book, and it's one of the books mentioned in the reading list. So I'll go through some of those now. And then if time permits, we'll go and look at these equilibrium examples. So this particular sheet that I'm going through is here in Blackboard called fbd.pdf. So that's the file which contains these examples that we are going to do. Okay, so remember what is free body diagram? As we showed two examples on Monday, the bottle and the stand and a pair of scissors. And we said free body diagram is absolutely important because that leads us to design, and we can assess the strength of the part of an object, and accordingly we design it. So free body diagram also, I emphasized, is not unique. It will depend on what the problem you are trying to solve. Now, one of the things about free body diagram that we can say clearly is that whenever you remove a support or another body, for example, if two are attached, then you have to replace with an equivalent force interacting force there. So force, I mean in a general term, that could be a line force or a moment, for example. So which will be clear if we start to do some of these examples now here. So this diagram shows what they said incomplete free body diagram. So the first one, it has got a bell crank supporting a mass M with pin support at A, and a flexible cable is pulling it in this direction. So the weight of the block is given as mg. Now in this problem, assume there is no self weight if not mentioned explicitly. So there is no self weight if not mentioned explicitly. So you may ask here, what about the weight of this crank itself? Okay, so that we are not considering for this problem. So weight of this block is mass times g, mg, acting downwards, and this cable is shown by a tension force T. Now we have removed the support here, the pin support. So what do you think I should replace here as the force by? So if you think about this point is free to rotate. So there would be no resistance to rotation. So there would be no moment. But it will be providing a force resistance or the resistance to movement. For example, this point, the pin cannot go down or up for that matter, or cannot go horizontally, left or right. So as a rule of thumb, always remember that if any movement is restricted, there is a possibility of reaction forces. So this pin restricts movement in the vertical direction. So there is a possibility of a vertical force. Okay. Now this could be up or down, Now we could see that the weight is acting downwards, so most likely this force would be acting in this direction. Similarly, this pin also stops the crank to move horizontally. So there would be a reaction force offered by the pin here. So again, it could be going from left to right or right to left. Now, as you can see, the tension force is shown going from right to left. So that must be balanced by a force going from left to right. Now, the direction of this is not, strictly speaking, important. Why do I say so? Because if you choose one of these forces in the different direction, once you do the equilibrium, then the right direction would come. For example, if you took the vertical direction going downward, then if you do summation of vertical forces 0, then you'll see that reaction forces would come with a negative sign. So that means you alter your direction. So the direction is not important, but the important is to identify the possibility of the forces. Now this pin would let it freely rotate the crank. So there would be no moment reaction. Now these are the forces I call reaction, because this is what this support is giving to the pin. Whereas the crank itself, so if I draw the pin here, if I draw the pin there, then on that pin itself, forces would be in the opposite direction. So it will be, so this force would come like this. So if I say this is the vertical force, so that would be V. And if this is horizontal force, then that would come like this. So these are equal and opposite to act on the pin. So on the triangular block here, I'll have a vertical force downward, which makes sense because that's what the weight of the block is going to do. And also it is pulling towards the left, so that means a pulling force to the left would be given onto that block as well. In return, this would give a reaction force. So whole point of free body diagram is that once we have removed the support, so these two forces act as a representative of the support. So now we can analyze this part of the crank and solve for the strength of it, stiffness of it, and then design accordingly. So that would complete the free body diagram for this part. Now, okay, the next one. Is this clear for everybody? Yeah? Okay, good. Now, I want your help on the second one. Okay, so the second one, you have got again a control lever applying a pull force P upwards, and again that is joint at a point over here. So it has shown by a force like this. Is this correct free body diagram? Yeah, go on. Is this free body diagram correct or complete?
This is not correct and this is not complete.
Oh, why do you think so?
Firstly, we need to have ourselves a reaction force at O.
Yeah, so this is the reaction force they are saying FO.
Yeah, no, there's no reaction force that's counteracting the down force that's applied over here, FO.
So the force, you are applying a pulling force P, so the reaction force is downward, so counteracting.
Fair enough. What about self-weight?
So self-weight, I said, forget about that for the time being.
I don't have to consider it as not explicitly mentioned. The force will be pointing towards the pin and not initiating from the pin.
So this force is going to point towards the pin.
The left part
Yeah?
will be pointing towards the pin, so it's an actual force.
So instead of from pin to downwards, what you are saying, it could have been from there to there. That's a very finer point. In this case, it will not make a difference. So point of action of the force is not that important for this class of problem. It's the direction that is important. So good point, but not exactly relevant here. Horizontal. Do you think there would be horizontal reaction force? Yeah, that's very good. But if I put a horizontal reaction force, then is there any force from there? No. Go on.
Wouldn't there be friction in the rivet connecting?
Possibly friction. So how do you represent that? But first of all, you need to think about whether this, as it is shown, whether this is under equilibrium or not. Is it under equilibrium? So if P is equal to F0, for example, so summation of vertical forces, one going upward, one going downward, same amount, that's it. Is this under equilibrium? No moment, because if you think about this, one force is trying to put it up and one force is pulling it down. So it is going to rotate. So there is nothing there to stop that rotation. So this is not under equilibrium under these two forces. So the pin there must be providing what you said through friction or the other means, some resistance to the rotation. So if you consider this is the pin, the forces would try to rotate it in the anti-clockwise direction. So the friction or some other one must be put a resisting force in this direction, resisting moment in that direction. And this resisting moment, if you call this is M, you could say that is the M is nothing but, if this distance is D, for example, that would be P times D, for example. So then it is under equilibrium. So both things you need to consider, whether there is any linear movement or rotational movement as well. Then only you will come to the conclusions of whether something is under equilibrium or not. Okay, is this okay? Fine. Go on, ask.
This weight as a factor.
So the weight of this one?
Yes.
Yeah, I'm assuming weight is, these are weightless in that way, to keep the problem simple. Okay? So assume there is no self weight on this problem, if I don't mention it explicitly. But if there was a weight there, then that will act through the centroid. Okay, next problem 3, boom OA of negligible mass, so I'm saying it negligible mass compared to the mass M, hinged at O and supported by hoisting cable at B. Now of course if you try to visualize the problem, so there is this boom and it is added with a load at the tip. So under the load, what will happen? This will try to go these directions, because the load will try to make the boom to rotate about its hinge point. Now the job of this cable is to keep it at that position. So this cable must be pulling it with a tension force. So this seems to be all right. Weight of this block is M times G. That looks all right, going downward as due to gravity. So what about point O? Do we need any force there, reaction force there, to make it under equilibrium? Yeah, go on.
Say what that guy said.
What is that? I didn't hear it.
I think the man said that there should be a vertical force up there in order to balance the.
Okay, so there is a vertical force there to balance it, this one, as well as some component of tension. Will there be a horizontal force? So there would be, because this tension is there in this direction, So there would be a horizontal force acting in this direction. Is this complete, this free body diagram? So one way to think about is this point, of course, it is if the magnitude of T and mg is such that they balance the rotations. So the moment of T and moment of m are in the two opposite directions. So they would probably balance each other if the distances are appropriate. So these two forces, whatever the magnitude would be, that would balance this whole system. So that's a complete free body diagram. Next problem I gave it as a last year's final exam paper. So this came in the last year's, this was online paper. So this problem was there in last year's paper. So you have got a crate of weight mg, and this is resting on to a vertical wall which is smooth. So this is a smooth vertical wall, and this floor is rough. So whenever you will see smooth or rough, difference is smooth will have no friction. Smooth means no friction. And rough normally means we are prompting you to think about friction. So if there is no friction, any reaction force from the surface will be perpendicular to the surface. Okay. So if this crate is leaning against the wall A, reaction force from the wall A would be perpendicular to the wall surface, so horizontal. Whereas mg is the weight acting downward, of course. So the reaction force from the bottom on the rough surface would be on to going into the upward direction. Now question is, do we need any horizontal force here, or is it balanced? Yes?
We need a horizontal force here.
Yeah, which direction?
Friction to the left.
To the left. Great. That's great. So this is due to friction. And that is complete in terms of the free body diagram. So this will come from friction, and this would balance probably this reaction force, and mg would balance this force. Now you need to think about the rotation as well. So these two forces are not known. If you take moment about this force at this point, then mg will create an anti-clockwise moment, whereas this force A will create a clockwise moment about this point. So there is a possibility of balancing those each other. If mg was on this side, then that was not the case. Then possibly you are looking at a different forces. So then that could be 0 or otherwise. Okay? So that means it will topple probably. So it is not stable. Problem number 5. A loaded bracket supported by pin connection at A. So that means this point is fixed. And then you have got a slot which is smooth. Smooth means there is no friction, and there is a pin attached onto that blue board at the background. And then you are pulling that bracket with a load L in this direction. So complete the free body diagram. Now of course this pin and the slot, the surface is smooth here we say. So that is a smooth slot. So that means no friction at this point. So any reaction force would act perpendicular to the surface. Now what about the reaction force at point A?
I think there might be a need for a reaction.
No reaction you think? What about the vertical and horizontal forces? Is there a possibility?
It's because of A, because the load L is pulling
Okay?
And again, there is A restricts the movement.
Okay?
Restriction of movement.
So I take your point. So I can put two forces, but it may happen that B and L are so arranged and their angle that these two reaction forces would be zero, for example. That's a possibility. Okay? But think again. Would that be so? Because these two forces can cancel each other only if they're acting along a single line.
So they cannot cancel each other due to the fact that
They are at a different angle.
the directions of their actions are not parallel.
Okay, so and if there is a parallel, then there would be a possibility of a moment here, but they are not parallel and not along the same line, so it's most likely point A would have some reaction forces. Is that okay? Okay. Yeah, some components can cancel, but there will be some components should be left over, for example. Okay, so what about this side? Are you okay? Yeah? Okay, so these are a little bit sort of slightly warm up problem. These ones are slightly tricky because either they are wrong or incomplete. So the first one, you are pushing a lawnmower of mass M being pushed up at an incline theta. So can you say what is wrong? First one. Yeah, go on.
An incredibly noticeable mistake over here is the location of MG. MG does not act perpendicular to the slope. It acts directly downwards.
Absolutely. So mg would act in the downward directions. Okay? That's good. That we have done one correction set already. What else? What else? Probably of friction. So friction at the surface, which direction it will act? So opposite to the direction of movement. So if you are pushing it up, so the friction would act in this direction. What about the load? Load is that mg that's coming down. What? Oh, the pushing load, you mean. That is there, P. That is there. That you are pushing that load with a P, so that could be there. That was there. Is that what you are asking? Okay, thank you. So that load is there anyway. It is shown, and then the weight mg is downward, so that's wrong. And then reaction force is opposite, and the friction force in that direction. Next one, yeah, go on.
There is a force P, right? So will that create a reaction force within the body?
Yes, yeah, of course it will P, you are putting the force, but that it's you have to take a system here that you have isolated only the roller and the crank, for example. So that's it. So that will give you the force in that. So if you separate it out the crank, for example, so the crank would get a reaction force in that direction. A pry bar lifting a body A having a smooth horizontal surface. That means this surface is smooth. So this is smooth, the smooth of part A. But bar rests on rough horizontal surface. So this surface is rough. So what about the free body diagram? Now the bar itself is shown, the load P is given, weight R, is probably, if this is mass m, that is equal to m times g. That looks right. And what else? The reaction force N shows downward. Is that right? It should be upward, isn't it? So this should be upward. Is that it?
Wait, sir?
Yeah?
Shouldn't there be a reaction force at P due to the load?
No, you are putting that load in that point.
Wait, so N is the reaction force which counteracts both R and P?
N is the reaction force from the ground to the bar.
Yeah.
And then you have got, of course, you can see there is a possibility of friction here. And you can look at this P is inclined towards the right. So possibly a friction force would act in the opposite directions of this, which is in this direction, a friction force. So a friction force would act in this direction. Okay. A uniform pole of mass m being hoisted into positions by this cable. So cable force is given by T, weight of this mast is mg, acting through the middle, and then of course this notch on the ground R. Is this complete or not? Sorry? There? No, if you don't have the tension, then the pole would just go into the ground. So, of course, you need to pull that with a tension force, yes. Yeah, so there would be a friction force at this point. Number 2, okay. So, because this force has got a component, if you think about, is going that direction and this direction. So that force must be balanced by a horizontal. But I know if you look at intuitively, it feels like the pry will slide in this direction. Yeah? But it is just that you have to think about the force that is going this direction. So it will probably give the movement in these directions. So the pry will slide to the right under this force. So this is not really balanced because, yes, mg could be balanced by this reaction force and this component of R, but definitely there is a tension component horizontally. So at this point in the notch, there would be a horizontal force acting at that point as well. Okay? You have understood up to here? This one? This point? Yeah. So if you consider this m, there are two forces shown here. That mg acting downward, so that can be balanced by this vertical reaction force. And this tension in the cable, you can think about this is made up of two components, one horizontal and one vertical. So the vertical bit could be registered by this part of it R. So R could be made up of this mg plus this vertical component. Now this must be then need to be balanced by here. So if you say this is a TV and this is TH horizontal, so R is mg plus T vertical and this is T horizontal. Have you understood up to here? Anybody has got any question? Yeah, go on. At this point, it's just that one. Yeah, this is the friction force. Yeah, this is the friction force. Sorry. Yeah. I should use different color. It's confusing. Okay. Now, have you understood everything so far? Go on. Oh, thumbs up. I thought you didn't understand. That's okay. So then if you have put your thumbs up, this is the difficult problem. I ask you to think about it. So you have got a frame, or here two parts of the frame, they are connected by pins. So that means they are relatively, there is no moment at those points, free to rotate at those pin position. So you have got a vertical bar and you have got like an angle. And they are connected into this position. So they want to analyze this angle. And this is the free body diagram somebody has drawn. Is this right? Is this complete or no? No.
I believe this is incomplete.
Incomplete, yes.
There should be a reaction force at A,
Yeah, so there would be a reaction force A. Which direction?
upwards.
So the reaction force at A would be upwards, you think?
Yes, reaction.
Okay, so let me give your suggestion slightly differently here, or shall I use another piece of paper? I think this is slightly needs your thinking. Okay, so this is the angle, and what you are saying is this would be upward, and this is the right hand direction, okay? And that's it? So where B should be towards the left in the otherwise direction. Is that all?
It is still weightless.
The bar is weightless. It has got only one force F there. Could be no horizontal force here. So how that force will go? So that means there will be no horizontal force anywhere in there. Go on.
Maybe there's a upward force of B and a leftward force of A.
So you want to add another two forces onto it.
No,
So I don't get that one, right? So you say upward force at this point
yeah, and a leftward force of O.
and leftward force at that one. Is this under equilibrium?
Yeah, I don't think there is a vertical action.
You think there is a vertical reaction. So point is, this is the whole point. If you start to think part of it, it is not possible. You cannot get that free body. Here, you have to go back and forth. You have to consider the whole structure, stripping off of the support and get couple of reaction forces. And then from there slowly build the whole free body diagram. So let me show you how to think about this problem in a manner. So first of all, what I'll do is I'll strip off these two support. I'll say, okay, I want to know what are the reaction forces onto the ground. Because remember, any force you apply to any object ultimately has to come to the ground, or the support, whatever. Ground is one term, but it need to come to the support. So I will draw this free body diagram of the whole structure first. So this is the bracket 1 to 1. So you have got this pin over here, and then you have got, this is the reaction force into there, and I have got a force shown here in this direction. Now of course there would be two reaction forces into under this one. Now what sort of reaction forces I am expecting at these 2 points? Upward, both upward. What about the horizontal reaction force? Yeah, go on. That's a force you are pulling, that somebody is doing that for. Somebody is trying to destroy that assembly, for example. That's the given. So it is probably attached to another machine, for example, or another point. So force towards the right here. Going, so will that be under balance then, the whole thing? So that equilibrium means summation of horizontal forces has to be 0. Summation of vertical forces has to be 0. And the third one is very crucial. The moment about any point is 0. So if you think about the third one for the time being and take moment about this point if you start to take. So take moment about this point. What is the moment due to F? Is it a clockwise or anti-clockwise? It will create a clockwise. So the reaction force on point B could be two. One vertical direction, one horizontal direction, right? These are the two possibilities. It could be both or could be either. So at point here, there could be two reaction forces. Now if you consider the moment due to this point F, that is going to create a clockwise moment. That must be balanced by this reaction force, because these are the only two which can resist that reaction, that rotation. There would be, of course, reaction force here, but they would not be able to provide that rotation if you consider moment about this point, because moment of these two forces would be 0. Similarly, moment of these horizontal forces would be also 0 if you take moment about this point, because this force passes through that point. So moment of this force, and that force are all 0. So only one candidate is left to resist the rotations, a clockwise rotation. So which direction you think the vertical reaction in this case going to be? Upward or downward? It has to be upward. So because only then this would be able to resist that force. Okay? And if you do little bit of dimension, if you give, let's say this distance is A and that distance is also A, then F time, and this distance is also A, all the dimensions are the same. Then if this is F, then that is F times 2A is the vertical, the moment. That must be balanced by A times F. So this should be, possibly would be twice F. So twice F times this distance must be balanced by F times twice A. So that is twice F. Now if this is twice F, what do you think this vertical reaction would be? Because there is no other vertical forces except that. So then it must be balanced by, for vertical equilibrium, a twice F in this direction.
Both F and the reaction force are the same.
So if let's take this point as point A. So if you take moment about point A, so if you take moment about point A, so you have got two forces. One is, say this is point A, and you have got here the force F is acting. So at a distance of 2A. So what is the moment? Is force times the perpendicular distance. So the perpendicular distance for this force is from here to here, so which is F times 2A. Similarly, this force times the distance, perpendicular distance, must balance that. So this force must be twice F. Yeah? So if this force is twice F, then for vertical equilibrium, you must say that that force would act twice F in this direction. So we have somehow got these two vertical reactions sorted. So you could see that possibly this is correct then, because that shows downward in this point, which is what we are getting from here as well, a downward force at that point. We are getting a downward force at that point as well. Now, what about the horizontal forces? What we are going to do about that? The reaction forces. There must be something because F has to be balanced by these two. How we are going to get the horizontal forces? Yeah, but I'm asking about what would be these two forces. Yeah, but I mean to give you what I mean, it could be F in this direction, it could be F in this direction, 2F could be this direction, F over 2, F over 2, F over 3, twice F over 3, any combination, as long as summation of the horizontal forces from left to right and right to left is 0. But how do I find out what are the forces into these 2 points? Very good. That's what you have to think outside the box. There is a hinge there, and a good attempt would be I could consider this part separately, and of course on this part there would be some reaction force here, some reaction force there. I don't know, but I know there is a force twice F in this direction, and I know there would be a force horizontal there. So for this angle, these are the 4 forces. And I also know if I call this point as point B, moment about point B is equal to 0. So that means the moment due to this force is 0 because it is passing through point B. Moment due to this point is 0 because that is passing through C. Now, 2F is creating an anticlockwise moment. So that must be balanced by a clockwise moment in this direction. So what would be this force then? It would be simply 2F in this direction. So once I get 2F, I put it back here. This is 2F. What do you think this force would be then in this case? F in this case. Now you couldn't have predicted this would be the F. You are pulling it in this direction, that would be F in this case, unless you walked backward and forward in this way. Yeah? It's a little bit tricky, but what we have done is we have considered the whole thing, and then we have gone into bit of it in detail. Once you know this one, then it's relatively straightforward to find out how much this would be. This would be 2F upwards, and this would be 2F down in that direction. So you could complete this one as goes like that and goes like this way. So this middle one. Yeah. Okay. So your question is why this bit is twice F. Okay, let me draw that bit again. So yeah. So we have got a force here acting at this point like F. Now that must be, this system must be balanced by 4 other forces. So 4 other forces are as follows. There could be a vertical force there, there could be a vertical force there, there could be a horizontal force there, there could be a horizontal force there. Now we need to find out all these 4. So now we'll use our strategy. If I take moment of all the forces about this point, then moment of this force is 0, because that is passing through that point. Moment of this force is 0 because that is passing through this point. Moment of this force is 0, that is passing through that point, because even if it is going left to right, it is going to hit that point, or even if it is going to right to left, that will still be 0. So only one is available, that one. So if this is at a distance, say twice A, F times twice A must be balanced by A times the force. So if this reaction force was, say, R, then R times A must be equal to F times 2A. Let's say this distance is R. So the moment about this point is R times A, which must be equal to F times 2A, because this distance is, how do we calculate moment? Moment is you extend the line of action of the force. So this is the line of action of the force F, and you drop a perpendicular to that line of action of the force, and you measure that distance. So this distance is twice A. So F times twice A is the moment about this point. Is that clear or no? No? This is absolutely important. You get the idea of the moment. Yeah, you raised your hand.
So in blue questions like this, we have to assume that the whole thing is in equilibrium?
So it is each and every part of it is under equilibrium. Yeah. Okay, so this is much more basic that you need to do. So if a force is acting at a point like that, so this is the force, and you want to calculate moment about a point, let's say here, point O. You want to calculate moment about this point. How do you do? You extend the line of action of the force in both directions and drop a perpendicular to that line of action of the force and measure the distance of this perpendicular. So if this distance is a d, then moment of this force about this point is F times d. Okay? So complete this one. This one is fairly easy. And before you leave, I just want to show you a few things. So equilibrium examples, I couldn't do it now. So what I'll do is I'll upload the solution, but don't look at the solution, please, because you will not get anything if you look at the solution. And finally, there is one problem where there is a small video which I will make it available. So see that video as well. Okay? And finally, before you leave, just give me one point. Just 1 minute. If you go to the revision folder, you will see the lecture notes. Have you had a look at that? So now you should be able to follow the lecture notes, what we have done so far. And then from the next week onwards, we are going to look at these lecture notes and solve tutorial problems. Okay, thank you.
Traveling to Manchester, I read yesterday. So is everything on Blackboard, which I can...
Everything is on Blackboard. Everything is on Blackboard. Thank you.
Just one thing. If we're not told whether or not a surface is rough or smooth, do we assume it's rough?
Yes.
Okay.
Yes, that's right.
For next week's lecture, so you'll be uploading the slides beforehand.
Yeah. So for probably this weekend you will get for the Monday's lecture. Yeah.
So will there be any tutorial before next week?
So next week we have got a tutorial on Friday.
Okay.
So Friday we have got tutorial. Tutorial, the way we'll run is, I'll give you the tutorial problems beforehand. You attempt it, and then here is that we'll have 3 or 4 GTAs and myself. Then we'll go around and see if you have got any difficulties, for example. I think one of these rooms there, maybe lecture theatre B or something.
Okay.
So not a flat space, but one of these spaces.
Thank you.
Or is this thing
Yes, I hope so. I hope so. It should be
Oh,
recorded.
it's because of me. Oh, it's because of me not focusing so much during page
I will probably this weekend do scan these and put that on.
I already saw them.
You have already got them. Okay.
Yeah, they're already on the net.
Okay, good.
So for page 2, question 45. So for page 2, question 4, I have to. This shows that I can add to a free body diagram. And in this free body diagram, I have to assume that this force is the moment everywhere.
Yeah.
So the
So
moment.
you find the reaction forces here due to this one. So you think about this as a whole system to start with, and then go to the separate bit.
Okay, so I have to think about this whole system, and
Yeah.
then I have to go to this separate bit.
Yeah, yeah.
So if I wanted to complete this for a question,
Yeah.
so I have to assume that all of these are. So are they going to tell us the distances?
Yeah, possibly.
So I have to assume. So I have to assume that the moment around about this and the moment about this are equal.
Yeah.
So I'm gonna be seeing the recording again.
Yeah. Yeah.
Thank you very much.
Go on.
I don't understand about this one, so it's a equilibrium.
Yeah.
body.
Yeah. Yeah.
And where's the pivot? Is this the pivot?
This is a pivot. These three pivots as well.
Oh,
So
and,
this is like in
and,
the air.
no, I
So
know
in
that
the hinge in the air.
The clockwise moment.
So this is in the air, and whereas these are on the
And
ground.
this force is F, and why these two forces are 2F?
So if you think about this force will create a moment, force times this distance, which is 2 times, say if this is 1 centimeter, so F times 2 centimeter. That
times.
yeah. So F times this distance, which is half of double of this distance. So this force must be double of that
All right. And,
to resist that moment.
and how to balance this force?
So
It's-
then
it
you
is
look
from-
at into step by step that we did all these steps here. Once you get these, and then you look at a small one first, and then that will give you the horizon.
I just want to take a photo. Okay.
How you are finding structure so far?